Hey everybody. Today we're talking about z-scores. Z-scores, also known as standard scores, measure the positions of values in a data set. And a z-score of a value is just the number of standard deviations by which that value is above or below the mean. As a simple example, suppose we have a set with a mean of 50 and a standard deviation of 8. And we're looking at a value in that set of 62. This value is 1.5 standard deviations above the mean. So the z-score of that value is 1.5. Here's the formula for computing a z-score. It's x minus mu over sigma, where x is the value in the set that you're trying to get the z-score of. So the numerator here, x minus mu, is just in absolute terms how much above or below the mean that value x is. Dividing by sigma takes into account the spread of the data. Something that's above the mean by a little bit in absolute terms matters more if the spread of the data is very small. Z-scores are a particularly appropriate measure of position for symmetric distributions and especially for bell-shaped ones, for normally distributed variables. When the data is skewed or has outliers, the mean and standard deviation aren't really very good measures of center and spread respectively. And since the z-score is based on mean and standard deviation, it becomes a less reliable measure of position in the data set. Z-scores are particularly useful when we're comparing values in different data sets, like in this example. The mean height of adult men in the United States is 69.4 inches, and the standard deviation is 3.0 inches. On the other hand, the mean height of adult women in the United States is 64.2, and the standard deviation is 2.7. Which is more unusual, a man that's 64.2 inches tall or a woman that's 69.4 inches tall? So what I did there was, for each one, I took the mean in the other gender. Let's compute some z-scores. For the man, we get 64.2 minus 69.4 over 3.0. So we take that individual man's height, we subtract off the average height of all men, and then after we've done that subtraction, divide by the standard deviation. We get negative 1.73, indicating that this man's height is 1.73 standard deviations below the average height of all men. We do a similar calculation for the woman, whose height was 69.4, being careful to use the mean and standard deviation for women, not for men. So that's why I have 64.2 and 2.7 in the z-score formula for the woman there. In this case, we get 1.93. So this woman's height is 1.93 standard deviations above average. Comparing these two numbers, we see that the woman's height is further from the mean. Her height is 1.93 standard deviations from the mean. The man's is 1.73 from the mean. She's the more unusual of the two. Generally, most of the data in any distribution lies within one standard deviation of the mean, and so z-scores do tend to be small in absolute value. As a convention, we sometimes consider data that lies more than 2 standard deviations away from the mean to be unusual, and data that lies more than 3 standard deviations from the mean to be very unusual. But you have to bear in mind, this is just a rule of thumb. It's not a sharp distinction. There's very little difference, for instance, in values with a z-score of 1.99 and 2.01, even though the first of them would not be considered unusual and the second one would, according to the standard on this slide. One last example. Should a 76-inch tall man be considered unusual by that standard? And just as a reminder, the mean height of men in the United States, adult men in the United States, is 69.4, and the standard deviation is 3.0. So we plug into the z-score formula. We take their height, subtract off the average height, and then divide by the standard deviation. We get 2.2. The z-score of 2.2 indicates that this person's height may be considered unusual by that standard, but not very unusual.